Hello, my name is Ethan Page, and today I'll be going over my binary search tree code for my CST382 Data Structures and Algorithms class. For this assignment, we had to build a binary search tree with a few basic functions, being insert, delete, a find a maximum value, and a traverse. There are a few bonus objectives. I'll get there later. To begin with, we have this menu here. We'll start with a custom array entry. We can enter any numbers we want here. I'll do 1 through 8 in a slightly different pattern. Then, let's see what the maximum value is, see if that's working right. It shows 8. Do an in-order traversal. 1 through 8. Now I can also delete nodes. Let's get rid of 3. And do another in-order 1, 2, 4. I can try and delete 3 again, and it will change nothing. 1, 2, 4. No error, we're all good. I can also try to add the same number over and over again, so let's just enter 1 8 times. Last time I'll enter 9, why not? Now if we go back to the in-order traversal, there's only one singular 1 there, and now there's also a 9. Now, this is basic functionality. I will show off the code in a moment. The bonus objectives that we had to go for was this second menu here. I can create 100 nodes, 1,000 nodes, 10,000 nodes, or 100,000 nodes. I opted to do this with a for loop and a random number generator between 1 and double the number of nodes, so there was some variation. Each one of these just takes us through a set thing. We'll start with 100. It creates the binary search tree with the values, lists everything there. Do an in-order traversal. As you can see here, if I scroll through, it's got all sorts of values. Traversal is completed, and it will clear. The binary search tree has been cleared. And I can do that with each of these. If I do 1,000, you see it takes a second there. Press any key to continue. Create 10,000. Takes a little bit longer. Get through. And create 100,000. This one takes a little bit longer. Doesn't seem to hit close to the 100,000 finisher, but it still creates quite a number. Now if I exit this, I can go back here and exit this. Let's have a look at the code. So, if we start down at the bottom with the main, this is where it starts. Here's the menu. This takes an array of integers, as was directed. Enter a value, counts down through this so that you put all the values of the array in, then we cycle through a for loop, inserting them all in. We'll get to that in a moment. Case 2 opens up the second menu, I'll show in a moment. 3 is the delete, which takes in an empty node and a value, that's why I specified. 4 shows max value, 5 does the in-order traversal, 6 leaves. The second menu is what did the 100, 1,000, 10,000, 100,000, and that used fairly similar code, except X was changed each time. This could have been written a little bit better, but I was in a bit of a rush, so I'm afraid I just used 4 case statements that were nigh on identical apart from X. It goes through a for loop up to the value of X, creating random numbers up to 2 times the value of X, and inserting those values into the binary search tree. And then tells you it does so, gives a pause, does an in-order traversal, gives another pause, and then deletes the tree. And it does it for each of the 3 variable types, or variable lengths rather. Now if you actually get into the tree itself, I've created 2 classes, a node class, templated, which is simple enough. All it contains is a value, key, and 2 pointers to a left and right child. I've also created a BST class, also templated, which has the function to create a new node, templated value, as you can see here. I can then insert a new node. It takes an empty node and a value, return a new node with that value, and then if value inserted is less than the key of the node, then it'll go to the left and insert there, and it does so recursively, so it will keep going down to the left until it is no longer less than, and then the same here for the right. There's also, as you see commented out here, a cout that I had for avoiding duplicates. This makes it so that if any equal values are inserted, they no longer insert duplicates. I would have left it uncommented, however, when I was doing the 100, 1000, so on and so forth tests, it got quite expansive. Now deletion takes, again, a node and a value. It returns a node. Now if the node key of the node that's being looked at is greater than the value, as shown with the comment here, it will go to the left child, and then this is also recursive. It will continually go down to the left, to the left, to the left, until it doesn't need to go to the left anymore. The same with the right. It will go and sort itself through until it is at the right spot. Once it gets to the right area, we hit step 2. It places the node with the child, if there's only one child. If the left child is null, then it creates a temporary node and grabs the right child, deletes the original, and replaces it with the temp. Or what's stored in the temp, rather. And then the opposite is here. If it only has a right child, then it does that. Step 3 is where it gets a little bit more complex, in a sense. If it has 2 children, then it needs to find the successor, the next greatest, which is always the leftmost child of the immediate right child. So I create 2 temporary nodes, the successor and the successor parent, set them both equal, and then this while loop steps through and just inches down to the left. Step 4, once they find the right one, once there is no longer a left child, once it is null of the successor, we know that's the right one. If it has a right child, we set that to the parent's left child so that it doesn't break the tree. And we set the original node's value equal to the successor's value, and then we delete the successor and we return with the new node. In other words, this doesn't delete the node that we were trying to delete as much as it rewrites the data that's inside and deletes the extraneous one. Finding maximum value is pretty simple. It uses a similar concept to the delete. As long as the node that we're looking at, stored in temp here, and the right-hand child of the node aren't nothing, then it will continue to step down to the right until there isn't a right anymore, at which point it will return the node found, for the maximum value will be at the rightmost point of the tree. Finally, in order traversal, this one is super recursive, but rather simple in such a way. You pass in the node, as long as the node isn't null, it will then try and go to the left, and that will call it again. And as long as the node isn't null, it will try and go to the left, so on and so forth until it can go left no more. Then it prints the data within that node, and steps up and prints the data within that node, and it tries to go right. And it continually goes left, and then it will step right, and then it goes left, and then it will step right, so on and so forth until it has been through the entire tree. This is the entirety of the code. It was actually pretty fun to do. I enjoyed getting all of this to work. Thank you very much. My name is Ethan Page.